So at the moment, we are working on the acidic set of conditions. And the idea here is going to be that this will react under acidic conditions to form a new product. And once again, we will start by drawing out a good Lewis structure for the reagents that are over the arrow. And so sulfuric acid is going to be one of those reagents, and methanol is going to be the other agent. We have plenty of both available. They can participate in the mechanism as often as they like. So you know that you have a very strong acid here, and therefore almost certainly this driving force for this reaction is going to be that this material will interact with the strong acid and will remove a proton. That's got to be the way this starts. This isn't particularly basic, but this is such a strong acid that this has to be the way things are kicked off. And so what we do now is take a look at the intermediate that forms. This should look familiar to you in a sense. This is rather similar to the mercury oxymercuration intermediates. This is similar as well in some sense to the bromonium style intermediates. We have not yet broken a bond in some sense. This oxygen is protonated at the moment, but it still has 3 bonds to it. Really, the way to think about this is that you have a large amount of delta plus at each of these positions, but the area where you have the most delta plus between the 2 carbons is really this carbon right here. Because this is tertiary in nature, this is the place with the larger delta plus. Obviously, the hydrogen carries a significant amount of delta plus as well. So if you are asking mechanistically what has to happen next, this is strained, this is willing to break open, but it does need something else to come by and open it first. This doesn't pop open on its own. Instead, this has to come by and do it. And so what's odd here is that this will be SN2-like in terms of the stereochemical outcome, but it's kind of SN1-like, much as I showed in the bromonium species before. And so the idea here really is that though we are drawing this as an epoxide, the bond to the tertiary position has weakened a little bit already. This is not yet broken. It still exists, but it's starting to get weaker, and that's because as we've protonated this, there's not enough electron density to go around, so things are being shared relatively unevenly. What that has a tendency to do is the tendency to flatten out this particular carbon right here. And so though it's technically still sp3, it is starting to flatten, it is starting to become more sp2-like. This is happening more at the tertiary position and less at the secondary position. So what we have here is something that's quite odd. SN1-like regiochemistry, but in terms of a stereochemical outcome, we get SN2-like stereochemistry. All that means, of course, is that the oxygen comes from the backside and kicks out the other oxygen, so we get an inversion of this stereocenter, which is why it's SN2-like. But in terms of the choice of which carbon gets attacked, you attack the carbon that has the greater delta plus. You attack the carbon that's more stable if you were to consider it as a tertiary versus a secondary. So the more stable carbocation gets attacked. In that sense, you get the regiochemistry of an SN1-like process, but this comes from the backside and kicks this forward, giving you SN2-like stereochemistry. The intermediate that we form first is, of course, going to be a protonated methanol having done the attack. And so what I want to point out here is that the OH that is unaffected has remained up toward you, whereas the methyl that was back has now become up, and the methanol has attacked from the back, so it is back down behind. That's what you form in the intermediates. Then another methanol molecule comes along and deprotonates, and so you isolate as the final material here the methyl ether that results from opening of the epoxide. So when you open an epoxide under acidic conditions, you'll get an SN2-like inversion of the stereochemistry, but it will happen at the SN1-like position. The place that would have the better carbocation, the tertiary position over secondary, secondary over a primary, and so on. It will operate under SN1-like regiochemistry in terms of where the new group attacks, but it will have SN2-like stereochemistry in that you invert at the position that gets attacked. And that's the result of opening an epoxide under acidic conditions.